Hello, my name is Michael Ortega. I'm a research engineer from the Laboratoire d'Informatique de Grenoble in France, and I will present you the second lesson about 3D interaction. This lesson is dedicated to the display of the third dimension on desktop configurations. So, we will see how 3D data is converted into a 2D image, what are the different types of conversions, and what is a depth cube. First of all, let's start with a definition. The basic entity of 3D data is the three-dimensional point. Its coordinates are generally composed by three values, x, y, and z, corresponding to its position on each axis of a direct orthogonal frame. Sometimes a fourth coordinate is used, but this is not addressed in this lesson. A model is then composed by a set of 3D points. They are defined in a local orthogonal frame like the blue one for the car. This local system has also a position, also defined like a 3D point in the global frame. As most of current display medias are based on planar technologies, especially in the desktop configuration, displaying a 3D object implies the use of a 3D projection function. This function converts the three-dimensional coordinates of a 3D point into two-dimensional coordinates in an image plane. From this, we can imagine a huge amount of different functions, but only two are quite often used. They are called perspective and orthographic projections. We'll see now their characteristics. The most used projection is the perspective projection. This projection is close to the projection of our eyes, so it seems realistic. Its principle is old because it is used from the beginning of the photography. The main idea here is represented in these figures. As you can see on the left, the camera has a center of projection through which the light can pass and reach the 2D image on the camera back. The image of the real world is then printed on this back. This theoretical principle is also called pinhole camera projection, and the plane on which the image is printed is called projection plane. In computer graphics, for displaying 3D data, the projection plane is placed in between the camera and the 3D data, like in the right figure. From the perspective 3D projection function, we can determine a region of space in the 3D data world that may appear in the image. It is called viewing frustum and correspond to the field of view of the camera. The main parameters that determine the frustums are the near plane, which is the distance between the camera and the projection plane. At the opposite, we have the far plane. It is the distance between the camera and the furthest object that will be displayed. And finally, we have the aspect ratio, which corresponds to the image height divided by the image width. It determines the projection plane coordinates. These three main parameters determine the field of view of the projection. All the objects out of the frustum are not displayed into the resulting image. As with the real camera, modulating these parameters changes the zoom, the focal distance, and so the resulted image. In the orthographic projection, compared to the perspective one, the projection lines are parallel to the line of sight. In that case, the viewing frustum is a rectangular parallelepiped. The near plane, the far plane, and the aspect ratio have the same definition than in the perspective projection, but they only determine the region of space in which the objects are displayed. There is no notion of zoom or angle of field of view. So now a simple question. Which one of these two images has been made with a perspective projection and which one with an orthographic one? Do you see what are the advantages of each projection? The answer will be discussed next. We will see now the depth cues. A depth cue is an information that our visual system uses to perceive the third dimension. It is extracted from the 2D information that comes to the retina. All these cues can be classified in four categories that we'll detail in the following: monocular and static cues, oculomotor cues, motion parallax and binocular disparity, and stereopsis. Monocular and static cues can be inferred from a static image viewed by a single eye. Most of them can be found in this image that uses a perspective projection. So please pause the video and take several seconds for trying to find all the cues. Five cues can be found in this image. The first one is the relative size of the objects. In this image, all the spheres have the same radius. However, their projected size depends on their distance to the camera. The closer the sphere is, the bigger is its projected surface. The second cue is the occlusion. A sphere A that occludes parts of a sphere B is closer than B to the camera. Occlusion allows to establish a relative distances between objects and the camera. The third cue is the shadow. Using light and then shadows gives another relative distance between objects. As we can see in the image, thanks to the shadow, we know that the red sphere touches the gray plane. The fourth cue is the aerial perspective suggested by the blur effect that the depth of field implies. Sharpened spheres are in front of blurred ones. The fifth cue is the linear perspective. This image suggests that the spheres are positioned on a regular grid. All the parallel lines of the grid meet on one point, called the vanishing point. Here there are four sets of parallel lines, so four vanishing points that are out of the image. These perspective lines help on perceiving the global architecture of the displayed world. So this is the list of all the molecular and static cues we saw. In the previous image, texture gradient was not presented. Most of the existing objects have a texture like wood, fabric, stone, brick, and concrete. These textures provide roughly regular patterns. Observing these patterns can help on perceiving the depth, but also the object orientation and position. The oculomotor cues are information sent from eye muscles. Accommodation is a physical stretching and relaxing of each eye length, caused by eye muscles when focusing. Indeed, the eye has to change the form of its elastic lengths in order to maintain a non-blurred image. The closer the seeing object is, the larger the lens is. Then this information helps on perceiving objects' distance from the eye. Convergence is the rotation of the eyes when they focus on the same object. The rotation information is provided by the eye muscle and it is proportional to the focusing distance. It's so another depth cue. Unfortunately, nowadays it is not possible to provide such cues with any screen, any stereoscopic display or whatever. The accommodation and the convergence are always fixed on the screen that displays the scene, and this scene does not move. In that way, it is important to know that because of that, sometimes, for some people, this lack of oculomotor cues in 3D displays results on nausea. We'll discuss this aspect in next lessons. The last depth cue we'll see is the motion parallax, which is a dynamic cue. When the user is moving, motion parallax causes closer objects to move more quickly than further ones. It occurs in animated 3D scenes or when both the position and the orientation of the camera are manipulated. Finally, coming back to the projection types, we can now present the advantages of each one. Perspective projection is close to our eye projection, so it is mainly used for all the realistic cues it provides, and often used for having a good overview of the 3D scene. Orthographic projection does not provide some depth cues, but this is exactly why it is used. Without depth cues, distances are not deformed by the depth, and the user can estimate the distance directly on the screen, for close objects as well as for far objects. This projection is also used for precise positioning and objects alignments. In conclusion, here is the classical 4 views configuration used in the commercial 3D modeling softwares. 3 views are orthographic projections along the common axis, X, Y, and Z, and one is a perspective projection for the overview of the scene. Now you know why they are both used.